Okay, so it should be recording. So this is the exam 2 review for third 320. So we're going to start by going over ROM. I'm going to grab a chair. So ROM stands for read only memory. So yeah. Does anybody have any questions about ROM? Because I feel like it's not too bad, but we'll do one quick question. Welcome in. So the main things you guys are going to have to worry about with ROMs are mostly just lookup tables. I don't think he's done anything other than that with ROMs. So we're going to go create a quick circuit. I'm going to just do an OR gate here. I almost made something else. Oh, I thought he was coming to talk to me. And then, I don't know, we'll put in version bubble here. We'll do A, B, we'll do B and C. Okay. How many ROMs are... Okay, we'll start with the very broad question. How many ROMs do we need to make this? What's the minimum amount? Minimum amount. One more time. The answer is 1, but yeah. This isn't what you probably want to do, but you could technically do it with 1 ROM. In the class, it's most likely going to have you use, I think it was a 4x1. Yeah, 4x1 ROM. So with this, we can split this up into 3 different ROMs. So we're going to go ahead and circle them. We're going to do Can you guys actually see that? Okay, somewhat. I'll switch colors. We can use this one. We can group these, and then we can group this gate. The way we use a ROM is basically make a truth table. So that's what we're going to do. We're going to start with the first one. That's also going to be a bad color. We're going to start with this one right here. So with this one, we have 2 inputs. So we're going to create a quick truth table, and then I'm going to call my output F. Why not? Then we're going to go to 0, 1, to 0, 1. Yeah. Okay. So since this is an OR gate, what is our output for F? Yep. So that will do that part, and then we'll go to the next one. So for this one, no, that's BC. BC, and then we'll call this G as our output. We're going to do the same thing. We're going to do 0, 1, 0, 0, 0, 1, 1, 0, and 1, 1. What's our outputs? Try again. So it's going to be 0, 1, 0, 0. Is that what everybody got? If you have any questions, ask now. Okay. Yeah, so since B is inverted, that means B has to be a 0 and C has to be a 1 because it's going through an AND gate. Because we're combining both the inverter and the AND gate. Yeah. So with these, you always combine the NOT gate. There's no reason to have a lot for just an inverter. That's just a waste of gates. All right, and then for the final one, this one's pretty obvious. We're gonna put our inputs as F and G, and then our output can be Q, I guess. 0, 0, 0, 1, 1, 0, 1, 1. What's going to be Q? What's Q going to be equal to? Or when's it going to be 1?
going to be 0, 1, 0, 0, 1, 0, 0. No, it's going to be a 1 whenever the output is. It's going to be a 1 whenever the output is. It's just an int. It's just an int. It's just 0, 0, 1, 0, 0, 0, 1.
Yep. So it's going to be 0, 0, 0, 1. 0, 0, 1. Because remember, this is just this AND gate. Because what we're doing with the LUT is we're splitting it up into smaller circuits so that we can make, instead of doing one giant circuit, we're splitting it up into smaller circuits and combining them. No. I mean, yes, technically. Yeah, so what we're doing here is we're just assuming that this wire right here is called F. And we're assuming that this wire right here is called G. That's all we're doing. That's just a temporary variable name. But the LUT that we're still creating is still just for the AND gate. So we can go create this real quick. Oh, let's not use white. That would make sense. Let's not use white. That would make sense. So we can put A and B into this lookup table. And feed it into here. So we'll have feed it into 0, 1, 0. And then this will be equal to 0, 1, 1, 1. And then we can have BC go into this lookup table. And then both of those are going to go into this lookup table right here. I'm not exactly sure how Bhatia does his, so maybe his lookup tables don't look like this. So just be prepared for that. Okay. Okay, so something like that. Yeah, just something like that. Okay, so that's gonna basically be it for Brahms. So go create a new page here. And what did tri-state logic? Yeah. So for tri-state logic, we have this. And then we should have another inverter going up this way, and then we should have an input here. And we should have an input. That looks really bad. Let me redraw that. That looks really bad. Let me redraw that. Oh yeah. Oh yeah. Yeah. I'll zoom in. Yeah. I'll zoom in. Yeah. Yeah. For like different like numbers of ROMs. Yeah, so you can obviously just use one ROM. So if you choose to use one ROM, you can just do all of this into a single ROM. You can do that. That's fine. You can. It might not be as efficient, yeah. So that's something that you have to consider. If you really want to, you can do just this, just that, just that. That's really, really bad. So I would highly not. Yeah. So generally, looking at his homework, I see that he gives you specific types of ROMs. So he'll give you a 4x1 or an 8x1 ROM. It's like, go make what f equals blank into ROMs. That would be an 8x1. I mean, probably, yeah. I'm not sure. Yeah. I'm not sure.
How would you do that exactly?
Yeah, so you see how we did this one right here? We do something similar. So we since I don't exactly know the values, I'm not actually gonna put in the values, but so we just do 0, 0, 0, 0, 0, 1. and then so on, right? And then we have our output here of whatever they may be, right? And then this would just be straight equal to Q.
To find our output, to be much harder, right? Because you kind of have to go through like all the right?
Yeah. Yeah, so the only way to really do that is actually write out the equation. So this would be equal to A plus B times B naught C. So if you multiply this out, you know that's A B naught plus B naught C. What is B naught C? Isn't that just that's not possible? Yeah. So so technically that's your answer. So if you want to do this, let's say right here it's 1 0 1. You'd put a 1 here. The rest would be 0. Or the rest would be 0. And then 0 and 0 1.
And also question, why is that? Because I know you mentioned something, right? I know you mentioned something here that
so sometimes it's more efficient if you shrink it down. So let's say, for example, yeah. So let's say, for example, you have 10 inputs, but the 2 of those inputs are only used in one tiny section. So instead of having 2 to the power of 10 possibilities, you can reduce that. So one of the ROMs, let's say, is 2 to the power of 8 because you have that. But the other one would be 2 to the power of 2. If you add these two together, that's going to be much smaller than 2 to the power of 10. It works very well in certain situations, and in a lot of other situations, it doesn't matter. Yeah. Yeah. All right. Anything else with ROMs? All right. Anything else with ROMs? And then we'll go back to tri-state logic. So the logic symbol for tri-state, that's bad. That should look something similar to this. So we'll say this is enable, this is enable not inverter, and this goes here. I think he probably made it similar to this. It could be a little different depending on your professor.
you just have the input, right?
Yeah. Did he get rid of the top?
Oh, yeah, just a C,
Okay. Yeah. Okay. Yeah. But yeah. So I'll just do it that way. So we'll get rid of this. Oh, that's too much. Okay. So we'll do C, we'll do D, and I don't know, we'll do Q. Why? Oh, sorry. Yeah. So who knows the truth table for this? Or let me. How many inputs do you have?
You have two.
2 inputs. How many outputs?
One.
Okay. So we'll start with that. So we know that our inputs are D and C, and our outputs are what? Q. Yeah. Okay. So we're going to do all of our possible values. Just going on out there. Yeah. So if we have a 0 0 going in, what is our output?
It's just going to be whatever D is to 0. Or no, it goes to a high impedance because C is at 0.
Yes.
So it just goes to Z, right?
Yes. I'm going to make sure that I don't.
It goes to Z, yeah. Because with tri-state buffers, if control is at 0, then the whole output just goes to Z.
Yes. So Z is considered an in-between value between 0 and 1, because in binary, your only values are 0 and 1. So to say that you don't know what the value is, you put Z, because it's impossible to know what that value is. because that value is being stored in a capacitor that's slowly discharging. So 0, 0, and 1. So, or actually, let's do 1, 0 first. Yep. So 0, 1. Yep. So 0, 1. Yeah. Yeah. Okay, technically, that's not correct because I drew an inverting one. But yeah, I'll let me erase the inverting one. But yeah, I'll get rid of the inversion. Sorry, we only use inverting in VLSI design because that's just how you make it. So I'm so used to doing it that way. But we're going to go grab this. We'll go duplicate it. We'll go draw an inversion bubble. Did he do a lot with this, or did he just say this is a thing? Did he do a lot with this, or this is a thing? Yeah, I assume so.
I mean, yeah, we never know. We never know.
Oh, yes. Oh, yes. Oh, no, just mute it. Only unmute whenever you talk. Only unmute whenever you're talking. Oh, I hope the other people could hear your questions, but unfortunately. Any questions about Tri-State or anything specific you want me to do with it? Yes. Yes.
When control is 1,
Yes, it's equal to D or the inverse of D. It's equal to D or the inverse of D. All right. I think we'll move on from Tri-State. Oh, latches, fun times. Okay. Okay. Okay, so we're gonna do an SR latch. So what type of SR latch do you usually use? NOR.
Yeah. NOR latches.
Do you care specifically, or does he care specifically?
We use both. Yeah. And then I think we covered NAND. It was NOR NAND. Yeah. It was NOR NAND. Yeah. It was NOR NAND.
Okay, so we'll start with the NOR SR latch. So it's called SR latch because there's two inputs, set and reset, or S and R. So we'll add those here. And then we have our feedback, like so. And then out here we should have Q naught, and out here we should have Q. And then to actually draw it out, it'll look like this. It'll have your S, you'll have your R, you'll have your R, then you'll have your Q, and your Q naught, and then your Q. Okay. So since this is a latch, that means it's asynchronous. Which means it doesn't care about your clock. It'll work no matter what. Yeah. Okay. So we'll go to the next one. Does anybody know what the truth table for this looks like? Because this will save you in your exam. So I would put this on your cheat sheet or whatever you get. So yeah. We'll.
It's like when S and R
Well, are you using the 2 or the 3-bit input? So there is a 3-bit input because, well, no. Look at this. Look at that. Look at that latch. How many inputs are there to the gates? What about the feedback? Yeah, there's technically there's 4, but we don't count the NOT. So we're gonna say that there's 3 inputs because you have your S, your R, and then your feedback from Q. Technically, because it's going into the gate. It'll make your life easier. Actually, not really, but I prefer it, so we're gonna do it that way. Yeah, but we're just gonna assume that the Q naught is inside here, because instead of just writing Q naught, it's already presented in the truth table, right? Because if you have Q, you know what Q naught is. But yes, technically that's correct. So we're gonna draw this out. You can do it this way. You can do it whatever way. Oh my God, whatever way you want for your exam. So we're gonna have Q and Q bar. I just realized I'm using bar. I assume everybody knows what the bar means. We'll just do read back.
I have a question really quick.
Yeah.
Isn't sometimes like the inputs or the outputs Q and Q bar, aren't they sometimes like depending on how we draw the circuit, they're in opposite places? So won't that like in opposite places as well?
Well, with the SR latch, it won't. But
like if you have like S and R, right? Like if you have like but then you have Q latch up and then the Q bar down, like does that?
Well, your Q bar will always be on the same area as you set.
I thought sometimes like they're flipped.
I believe for your NAND, it's flipped.
Oh yeah, it is for NAND. Okay,
it's flipped.
That's oh yeah, okay. That's gotcha.
But we'll get to that in a second. So I'm gonna go back. So for this truth table, since it's 3 bits, we're gonna have 2 to the power of 3, which is a lot. Actually, not that many, but yeah. Okay, so with this, if your Q is a 0 and your S and your R are zeros, what's the next Q gonna be equal to?
It's just whatever the previous is.
Yeah. So it's gonna be 0.
Because there's no change.
Yep. And then obviously Q inverted. And then if R is a 1 and Q is a 0 and S is a 0, if your reset's on, it's always going to be. If your reset's on, it's always going to be. So we're going to have 0 and 1. So now you have 0 and 1. Now a 1, which means Q is going to be a 1. Yeah. And then what about this one?
It's not possible.
Yep. So we're just going to do. We're going to write undefined. Yeah. You don't want to do it, but yeah. So next we're gonna do. We'll write 0, 0. So next we're gonna do when Q is actually on. So next when it's 0, 0. What's it gonna be?
It's just whatever the state Q is. So whatever the state 1 Q bar would be 0.
Okay, and then with reset it's gonna be a 1. With set it's gonna be a 1, 0, and then the same thing. Yeah. We're gonna do undefined 0, 0, 0. Oh, I should check the chat if anybody said anything. No one said anything. Okay, we're good. No one's said anything. Okay, good.
Wait, I'm sorry. Could you explain how you got?
The outputs? Yeah. So So if we look here, right? Yeah. So if we look here, right? You know what set does is it'll always make your output your Q as a 1. That's just what set does. So and then reset will do the opposite. It'll set it as a 0. So if we look at the first one, since set and reset are both 0, that means they're not contributing anything. So we just look at Q. We just do whatever Q is. But on the second one here, we have 0, 0, 1, which means reset is enabled, which means it has the highest priority. So we're gonna output our Q as a 0. And then similarly for the next one, set has priority because set is now 1. So then Q is going to be a 1. Does that make sense?
Yeah.
Does that make sense? Yeah. Yeah. Yeah, that's how I do it. Yeah, that's how I do it. Okay. Okay. Let's see what's next. I guess we'll go do the NAND SR latch. Oh, huh. No, the Q naught is still at the top for the NAND SR latch.
In some examples I was looking at, like in the slides, they were interchanged sometimes.
Okay. Was the set on top for that too?
Set was on top, yeah.
And the Q was on top?
Q was on top. Q was on top.
Okay, I'm not sure.
That's why I was confused, because in the slides, S is on top, and Q is on top, and S is on top, and Q is on top, and Q
I'm
bar
looking at the slides.
reset is. Oh.
Yeah, I remember seeing that too.
Okay.
I remember seeing that too. I guess it doesn't matter. But I guess it doesn't matter.
Doesn't matter. For the sake of this review.
Yeah, we'll just do what it says
Okay,
here.
we'll just
do what it. But I would have to check in on that. I'm not too sure. Because in my digital circuits class, we talked about SR latches for a day. Never said another word. SR latches for a day. Never said another word about them. So we'll do Q bar here. Then we'll do Q here. Then we'll do Q here. Okay, so so obviously these don't look the exact same. So you don't really have to worry about that. Okay, so these are going to be very similar to each other. So I'm just going to copy this over. Bring this down. Okay. So since these are very, very similar, the only difference is these two. These two will be flipped around. So we're going to go ahead and do that. Grab this, move it over here. I'll grab this, move it over here. And then additionally, these will be flipped to 1, 1. All right. Any questions on that one? Yes.
Gotcha, because yeah, you can't just do yes.
Yeah. I'm just looking at the next thing. Control. Okay, we're gonna go ahead and move on. So let's see, what's the next thing? Do you want to do the control one?
The gated one?
Yes.
Yeah. Let's do
Okay.
this. Let's do that.
Okay. So with this, we only have a few inputs. So we're gonna have our, actually, we'll draw this out first. We'll have our AND gate, our C, our other AND gate, and our R. And then we'll have our NOR, and then our other NOR. These will connect this way. This will be Q bar, and then this will be Q bar, and this will be Q. Yes. No control.
This is a gated, right?
Yes.
Gated, right?
Yes. Wait.
Is that what it's called?
Wait. Yes.
It's just called gated, that's right?
Yeah. So it technically could be a clock, but I wouldn't do it as a clock.
So you don't write C as a clock. It's just a C and C as a
Yeah.
clock. It's just because a lot of people mistake the C for clock. Right?
It can be a clock.
It can. Okay.
Yes.
Okay.
I don't like to use it as a clock because
Like for the previous one, isn't the like for the truth table for the NOR and the NAND, the NAND for the NOR and the NAND, the NAND.
I don't think so. Let me take a look. Yeah.
So for a
Yeah.
NAND, it's always one, except when one ones. Like just a logic gate, you know?
Yeah. Let's look. Yeah.
So for a NAND, everything is like for the truth table for a NAND, everything is one, except for one, right? So wouldn't it be undefined?
Okay. So I understand where you're coming from, but let's look at it. Let's look at the actual gate here, right? So if we look at the gate, let's assume that we had our value of 0, 1, 1 as our, so Q is equal, God, that's a bad color. Let's say this is equal to 0, R is equal to 1, and S is equal to 1. Okay, so this means that right here we have a 1, we have a 0, we have a 1, and we have a 0. Okay, so what's the output of that NAND gate, or NOR? NOR? Remember, it's a NOR, so not OR.
Oh, yeah, 0.
Yeah, so it'd be a 0. What about this one?
0.
It would also be a 0. So what happens? It gets stuck. So you can't do that.
Okay.
So let's follow the same logic for this one. So we see that it gets stuck at 0, 0, 0. So if we follow that same logic, we're going to set Q is equal to 0, S equals to 0, R equal to 0. So we'll have a 0, 0, 0, and a 0. So this is a not AND. So if we have did I mess something up? Oh, no. Yeah, it doesn't matter. So this will switch into a 1, right? Both of these will switch into a 1. So yeah, so we get a 1 and a 1 here, so we get stuck again. Any questions? Okay. I'm not sure, I'll be honest. That probably, yes, because you have the fluctuation in the gate voltages, but I'm not too sure what that exact value is. Okay, then I'll go, okay, now we're gonna come back to here. This is for your gated SR latch. Yeah, so we have our two variants. So this one is going to be your NOR, and then this one's going to be your NAND. Because of the NOR and the NAND. Okay, so we'll go ahead and do that. So we're going to have C, S, and R. Have 1, 0, 0, 0, 1, 1, 0, 1, and then 0, X, X. I'm shortening the truth table for obvious reasons, because if the control is a 0, then it can't work. If you want to use the larger truth table, feel free. And this will also be Q. I feel like I spelled that wrong. That's right. I guess that's right. I wrote it weird. Okay. And then I think that's basically it for the latches. Or I guess I can go do the same thing for the one below it. Can someone check if that's right? Think so. If I think those two just flips. I could be wrong. Or actually, let's just do math. So if we have a 1 and a 1, a 1 and a 1, not and will be a 0. This will be a 0 here. Our Q as a 1. So we have a 1 here and a 0 here. Not and will be a 1 here. And then this would also be a not here. No, okay, never mind. I'm pretty sure it stays like this. I could be wrong, but I believe if I did my math, that's how that works.
Is there a reason
So not necessarily. You can flip the truth table around. So so we can flip it around. We can move this over here. It's just that the more important values go. Either way is fine. Obviously, you have you don't care, so you don't have to do the rest of the values. Yeah. So if
like for the control. Like if you just have the control.
Yeah, so the control will make it so that it only works when it's a 1. So we already know that the circuit won't work if S and R are both 1s, right? Because that'll break the entire circuit. So ignore that term. Okay. So then if we have an S or an R as a 1, but C as a 0, so let's go do it. Let's go make an imaginary 1. So we have 0 here, a 0 here, and then let's say a 1 and a 0. So 0, 1 is what? That's a 1. Right? So that'll give you a 1. 0, 0 will also give you a 1. So let's say, then we just have to assume our Q value. Erase this stuff. Let's assume our Q1 as. Did I mess this up? No, Right. Okay. Our Q is going to be equal to 1, and our Q naught is going to be equal to 0. So we put a 1 here and a 0 here. This will make it so that Q is 1 and Q naught is still 0. You see how it just held its value? Yeah, that's basically all it does. It makes sure that you're holding your value. It might be easier for you to like walk through like the actual circuit. If that doesn't make perfect sense to you, try all the combinations.
I just said because like when the control is
0
0
and it changes to 1, like the output is still Q.
Oh, you mean from right here? From right here?
The control changing to 1 doesn't really change much in the output.
Well, if we look up here, right, we know that up here, we know that right here and right here, all it did is hold its value, right? We know that whenever S and R are both equal to 0, it'll hold whatever Q was. Right? So, keeping that knowledge, if we go over here, since T is a 1, we can basically ignore it. We know that the SR latch is now working. So following that logic, if we look at S and R, it's what? It's a hold. They're both 0, 0, which means it's a hold. It's following that kind of logic. But instead, let's say we go from can't use white. Let's say we go from 0, 1, 0 to 1, 1, 0. This is going to be equal to Q. Well, this is going to be equal to what's set? Set is 1. Is 1. So it's just because that's just the way the truth table set up. It's just because that's just the way the truth table set up. It does actually do something. All right. Any other questions about SR latches? All right. We'll move on to the next thing. T flip-flops. Oh, great. i.e. a T flip-flop. Okay. So since we're kind of like running out of time, so I can actually get to questions, I'm going to fly through this part. Let me know if you want me to stop. Okay. So or just show up to my tutoring hours later and I can explain it to you further. Yes. Preferably the today or tomorrow. It depends on. One's during your class, and then the other one's on Friday. Friday before our Fun 1 class. Anybody know when that is? Yeah, I think it's like 1 to 2:30, something around there. Or if that doesn't work for you, just text me on Discord. I can probably help you. So with this, a T flip-flop only works whenever the clock changes. So our two inputs are going to be clock and T. But it's not just going to be a regular clock. It's going to be the clock rising edge or the clock falling edge because we're only going to do the rising because we're only going to do rising because there's no inversion bubble at the triangle.
But wouldn't it be counted as like a level? Because you look at the rising and the falling.
Not with a T flip-flop.
Oh, okay, that's right.
It's all good. You should have played it out. I'm not going to draw that. Okay, so we have our clocks. Okay, we have our T. These are our inputs. And then your Q is going to be your output. I'm not going to do Q naught because it's obvious, right? So let's say that arrow means rising, and this arrow means falling edge. So we'll have T as a 0, T as a 1. This will be equal to Q, and then this will be equal to Q naught. Oh, sorry. Ignore everything I just said. This doesn't make sense. That's also rising. Yeah. That was, I figured something didn't make sense. That's what it was. Okay, next thing, what was next? D flip-flops. Okay, D flip-flops it is. Flip-flops it is. Did we even Let me go find it on here. Oh, there it is. Oh, there it is. Okay. Did we do a D-latch?
The D-latch just inputs the reset.
Yeah, that's all it does. Yeah, that's all it does. Yeah. Do you want me to go over it?
Yes, please.
Okay. Yeah. I have until 7:30, guys. So you have me until then, and then I'm leaving. Because I got to go somewhere.
Stay here till 10.
What was I doing? Okay, this goes here. This here. This will go here. It's a pretty rough sketch. Okay. Yes. Yeah, NOR based. Okay, so we have our two inputs of C and D, because a D latch only has a single input. So with that, we have C, D. We can do the 0 at the top, because someone was talking about that earlier. And then we'll have our Q here. So this will hold, this will be a 1, and this will be a 1. So D latches are very, very simple. If your clock or your control is off, you just hold your value. If your clock is on or control and your D is a 0, you input your D as your new value, and then then if D is a 1, you obviously input a 1. For your test, just have all of the ones he's taught you and just put a picture of it on your notes, and you'll be fine. What else? Anything else on this stuff? Okay. Oh, you guys are so lucky that those timing diagrams are difficult.
No way.
Sure, this is all the content.
No.
Oh, no. That's we still have one more thing to go over. Oh, FSM's like the important one too.
During the stage,
Converting to a table. What do you mean the bubbles? Like the actual like? You mean like this to that, and then that to whatever? Okay. Well, I have a lot of questions over that. I have a lot. What's up? Yeah, I have a lot of them. Yeah. All right, guys, let's go to the last homework I ever had for this class. See what happens. Let's see.
Could you do like one where you have like the word column?
Yeah, I have a lot of those. So I'm gonna let you guys know. I do mine a little differently because that's how I was taught. So you guys are gonna have to massage it a little till you get to the way you're gonna do it. I don't know. Professors love to say, "I'm gonna go massage this equation so it works the way I want it to." So I don't know. Let's see. Do you just want me to go over an example? Because I feel like it's easier to just go over an example. or like just start with an example and teach as like to start with an example and teach. Or is there anything specific that you want me to go over? Or is there anything specific that you want me to go over?
Lecture notes that are.
Yeah, I have the lecture notes here. Yeah, I have the lecture notes here.
Like at the very end of like at the very sequential logic circuits.
Yes.
That's like where sequential logic circuits.
Yes.
That's like where. You talking about that, or what are you talking about?
I have whatever Riyadh sent to me. It's six sequential logic design. PDF.
Did we even have any questions for this? Like, the exam has that channel? I think we have. The only thing that we really have, for like this is doing like a right is like.
Oh, okay. Yeah. Okay. Yeah.
I'm talking about.
Look.
Yeah.
Look. Yeah, I have that here. Yeah, I have that here.
Oh, I thought we were talking about the other ones. Oh, no, we were talking about the other ones. No. Oh, yeah. I sent the
Okay, so yeah, I'm just gonna start with the question because I feel like it'll be easier. So we'll do homework 5. Go to. Oh no, not homework 5. I'll go to homework 6. I'll go to homework 6. Then I'm gonna erase this because it makes me look stupid. Yeah. Okay. Well, we'll do 3.24. Yes. Yes. It's from a textbook. I don't know if it's your textbook. I could not tell you, but I can probably find it after. Yeah. So we see here that we're only creating the state diagram. We're not actually making the state diagram into actual gates. Have you done that yet?
We've done that.
Do you have to do that for your exam?
Yeah, we have to.
Okay, we'll do that later.
Yeah.
Okay, because that's
I
going
just
to
wanted
help.
to understand it how to do it first. Yeah.
So let's look at this word problem, right? So it says that we have an input x and we have an output y. So we have our input x, output y. So if we look at this, it says whenever x changes. So that means we have a state where x is 0 and a state where x is y. X is y as our one. At a minimum, we have 2 states from there. So does everybody know what an FSM means? Okay. So the word finite means that there's a certain number. Let's just have that in mind whenever we go over this. Just have that in mind. With this line right here, we know that there is at least two states. Then it says right here that y will become 1 for 2 clock cycles whenever x changes. So we'll start with that. We'll go create a circle here. We'll set that this is equal here. This x equals 0 here. Yeah, and then we're gonna go here. Yeah, we'll get there. Yeah, and then we're gonna have an arrow. This arrow means that what happens, or like what's the requirement to go to the next state. And what's up? Yeah, you're right. So the requirement is that x has to equal 1. But instead of writing x equals 1, we're just going to write x equals 1.
Last question before we continue. Is this for a melee or more? Does it specify or more?
I believe it's melee.
It's melee. Okay.
Is melee the one where it comes back?
I think they both come back, but just like,
There is a difference. Okay. Okay. Yeah.
And then slash 0, and then slash.
Yeah.
Inside the bubble.
This is how I was taught to do it, where you put your input in the circle and your output is outside the circle.
I like that. Yeah.
Yeah, that's how I've always done it. Yeah, I don't know how Batya teaches you it, but do it the way he does it.
Okay. Okay.
I mean, you can do it both ways. I mean, you can both ways for the right one. Okay, so let's look at the word question, word problem. We see that whenever x turns to 1, y should become 1. Right. Right. Right here, x changes to 1, and then y should. Yeah, it works. Okay. Yeah. So now we're going to set y equals 1. So there, we assume that every time that there is an arrow here, we assume that it's whatever is here times whatever is here up times clock up. In most of your classes, that's going to be an assumption. I'm not sure about Batya, but anytime I do it, just assume that there's always going to be a clock up. Okay. So right here with this x would be x times clock up. Okay. And then so since we don't change our input here, we just hold it here, and we go over here. So since we need it to be equal to 2 clock cycles, that means we also need to have another clock up here. But since it's assumed, you could also erase it. Okay, so now it wants it to return to 0 even if x is still 1. What does that mean? Any ideas?
Even if x is 0, loops back.
Yeah.
So you just draw from the first one, you just draw an arrow right back, you just draw an arrow right back to the first bubble.
Like this?
Like that.
So you're not technically wrong, but you'd skip too many steps. We will get back to that, but not yet. So we also have y equals 1 here. Sorry, I forgot that. So now we're going to create another circle. So this one is going to be our hold. We see here that y needs to be 0 even if x is still 1. So before we can go back to our initial state where x is equal to 0, we have to wait till x equals 1. Right? Yes, but x is your input, so you can change x. But let's say x stays 1 for a very long time. You don't want y to keep staying as 1. You want y to only be 1 for 2 inputs. That's what the question's asking. So to do that, we're going to pull an arrow over here. And this is only this. When do we want to use this other state? Okay, actually, so we're going to have 2 arrows. We're going to have an arrow back to our initial state. When what? When would we go back? Okay. What else? Because we also need to make sure that x. X equals what? Yes. This is going to be equal to x naught. We want to go back whenever x is equal to 0. Yeah. Go. Did I click something? Okay. Yeah. Okay. And then we also need to know what do we want to do for the other one? Yeah. So we're just going to have x here. This one? Yes. So we're going to set y equals 0 here. So now we're going to wait. So we're going to do the same thing we did with this. The same thing we did with this arrow here. Where we have x naught. We're going to do the same thing for this one. Because we're waiting till x is equal to 0 before we come back to the initial state, so we can repeat the process. Okay. So does that make sense, or do we have an issue? Yeah. Clock rising. That's assumed. That's assumed for all. So I could just erase it. No, because there's a chance that right here, in between these two states, x equals 0. You have to assume for every single case, the off chance that x equals 0. Okay. All right. How many people think we're done? Okay, thank God, because I told Riyadh that he was on the right track. All right, Riyadh. What? When I told you that we needed a circle before, why would we need that? Right. Yeah. Right. So remember how we did this? Why would we need this?
In case Y doesn't. If it doesn't change, if there's no change, if it doesn't change.
If what doesn't change?
If
Yeah. So, what is x currently in that situation?
No, it's a 0.
Yeah.
It's a 0 in that state because.
Yeah.
Whenever x changes, whenever x changes, Y. So if x is 0, then x is 0.
Yeah.
It just keeps moving.
Yeah. So if we look back at the problem, it says when x changes from 0 to 1. So we want to hold here until x actually changes to 1.
You're just holding that value.
Yeah. So remember that means at every clock cycle, every clock up, right? That the arrow means clock up.
Example that explains this the best is like a set of values, ones and zeros, and then you're asked to like locate certain pattern combinations.
Oh, I remember that. I was helping someone with that earlier. Yeah. If someone can bring me one of those questions later. Yeah. So if we follow, okay, are we done? With this, is this state diagram correct? All right, let's go from state to state, starting with this state right here. Is anything wrong with it? Okay, I'm going to give you a hint. So we need to make sure that our outputs for this have all possible values of our inputs. So since our input is just x, we need to make sure that there's an x leaving and an x not leaving. Yes, that counts as a leaving because it leaves right here, but it comes back to itself. Yeah, that's fine. You have to have that. Yeah, that's fine. If you ever want it to repeat itself, you have to have an arrow coming back to itself. So we're just gonna assume, don't care about what's coming in, we're only caring about what's leaving. So here, we need to make sure that we have all possible combinations leaving. Is that happening? This one? No. We're gonna start with the initial state. And we're gonna go state to state. So, anything you want to change? The answer can be that there's no change. Okay, correct. The second one, any change? No. So if we look at the question, it says that it only holds for 2 clock cycles. Each of these states is 1 clock cycle.
So the third one has to have a hold.
Well, we have this state as our hold. This is our hold.
Okay.
So I can label this as hold.
I was wondering because you mentioned it.
Yeah, but we can't have a hold right here, right? Because if we do, then we're holding y equals 1. But we want y to go back to 0.
Yeah.
So, right, so we checked that this is good. We checked that this is good. What about this last one? Or, I mean, this one. Sorry. Check our inputs. Have all of our inputs, have all of our bases been covered?
Well, your input for your x is going to input.
All right, raise your hands. Are we good, or do we need to change something? If you want to change something, or if you think we're good, raise your hand. We got one. All right, if you want to change something, raise your hand. Okay. All right, he's right. We're good. We're good. Yeah, we're good. Yeah. So if we look at this, right, we see that we have an X leaving and we have an X not leaving. So that's all of our possible bases because we only have one input. Or we hold, or we wait till X. No, give me 1 second. Let me write this. Okay, sorry, what's up, Colin? Okay, sorry, what's up, Colin?
We need a X and X not leave.
For this one? For this arrow?
Don't we need like, I thought you said.
Are you talking about this one? Yeah, sorry. Okay.
I thought you said we need an X and X not leave.
Yeah.
X and X not
So
leave.
we're assuming that. How do I explain this? Okay, so let's. Okay, so you know in Boolean algebra, if it's an x plus x naught, what's that equal to? Plus x naught, what's that equal to? Okay, so we're going to assume that. We're going to assume that there is a 1 here times clock up. Okay, and then for this one, it's times clock up. Right. So if there's nothing there, that means it just leaves no matter what. So imagine that as a don't care. It doesn't care what's going on. It'll leave no matter what. It doesn't care what's going on. Whenever there's a clock up, of course. Does that answer your question? Okay. Okay. And then lastly, we have our last one. Are we missing anything? All right, raise your hands for no. All right, raise your hands for yes, we're missing something. You would be right. What are we missing?
Isn't it whenever?
Yes. What do we do if we have an X? Yes. Correct.
You're holding for the X value to become X naught.
Yeah.
So it reverts back to X equals 0.
Yes. Yeah, it'll take some time. Just do a few questions and it'll
Another one. Oh, we're not done. Another one.
No, we're done. We're done. That's it. We're done. We're done. That's it. Huh? Oh, actually, technically, we're not done. Actually, we're not done. But we have to label our state. This will make it easier whenever you're actually making a truth table. So we do this in binary, of course, since we have 4 states. How many binary values do you need to have 2 states? 4 states. 2. I accidentally gave away the answer while I was talking, but we'll have 0, 1, 1, 0, and 1, 1. I chose those values. You can choose whatever you could possibly want as your state values. Just never repeat. Whatever you do, don't repeat them. Okay. For this question, that's going to be it. We'll get to one of the harder questions where we'll actually have to go do something.
More examples, please.
Yes. I need to see.
It is dependent on some. Something you just know that it's a more. So look at the way we showed it, and then if you want to fix it from.
You said it's a more.
Yeah, you know, I was really.
You know, we said it's a.
You said this was a more, right? You said this was a more, right? Did we say this was a more, right?
It's maybe. Well, I only have to do one. Let me see. Google Mealy or more model.
See the way the notations are written.
No, this is a more. So a Mealy model is determined by both the current and the current state and the current inputs, while a Moore model is only based on the current inputs. You see here, we don't care about whatever y is. We don't worry about what y is. We only worry about what x is. So if we look right here at all of our lines, we only have x. Let's say, for example, we had y here. Then that would turn into a Mealy model. Yeah. If our output is one of the requirements to go to a next state, then it would be a Mealy model.
This is slowly stumbling.
Yes. More examples. Moha. Examples. Moha. Yes. Your output requires your input, but your input doesn't require your output. For a more. For Mealy, it does. For Mealy, it does. Do you want to give me the question that you wanted? Do you want to give me the question that you wanted? Or okay. Or, is it? Yeah. Yeah. 3.25. It's a different question. Do you want me to go over it? It's a different question. Do you want me to go over it? Yeah, it's still an FSM. Yeah, it's still an FSM. I love how if anybody has Pedram, they're just like copying. I love how if anybody has Pedram, they're just like. It is what it is. Yeah, it is what it is. It's a good bit harder. Okay, so. Okay, we're gonna go do some guesses. How many inputs do we have? How many inputs do we have? Yes. Yes. Inputs, not states. Inputs, not states. Yes. The answer is 0. Make sure you read your questions, guys. Don't assume. Read your questions, guys. Don't assume. I knew someone would do it. I knew. And then you have 3 outputs. Okay. How many states do we have? How many states do we have? Anyone else want to say anything other than 4? Other than 4.
It says repeats, so wouldn't it be kind of like more than just 4? Or wouldn't it be like that?
It's 4. Well, right, because we have these 4. We go here, we go here, we go here, and then we just come back.
That's
Yes.
Wait, no, I thought Mealy was out. Wait, no, I thought Mealy was output.
No, Mealy is both input and output. Yes. No, more is just input. Mealy is both. Mealy is both. So you technically could force this to be a Mealy model. You could force it to be one. Should you? No, because you're wasting gates. But if you really wanted to, yes, you could force it. Mealy, no, more does not have the current state. The current state it's in. Mealy has both your current state and your current input. Yes. Yes. All of the ones that I have will always be more because my professor only did more. Okay. So I'm going to have you guys try to work it out on your own, and then I'll slowly start working it out. Yeah. Yeah.
So if the arrows are considered outputs, isn't the arrows are considered outputs, right? Or am I tweaking?
Okay, one more time. Yes.
I'm looking at
Yes.
the arrows from the arrows is the output.
No. So think of the outputs as like actual values. So you see here how I have 3 values here? Those 3 would be my outputs. No. So think if you're just arrows as your transition. What do you need in order to transition to the next state? And since here there is no inputs, you have nothing there's nothing needed to transition. You only transition whenever you have a clock up. Yes. Yes. What do you think? What do you think? Okay, yeah. The answer is a more because our outputs aren't required in order to go to the next state. Okay, and then I'll go to the last one. Real quick. And that should be it. Yes. Yes. Yeah, that's it. Yeah, that's it.
Wait, I know why. What are the states? But why are you doing the state? What are the states?
So whenever you do this, like whenever you actually transition it into a circuit, you need to label what state you're in. So you're going to have a variable, let's call it S1 and S0. So this will be 0, 0, 0, 1 for your certain states. Yes. Basically, yes. Yes.
Oh, okay. So wait, I guess I was a little scared of it because I looked at every single example that we have, and the notations just made everything scary.
Yeah, when someone brought me the notation that he did, it took me a while until I figured it out, and then it made sense. Yeah, that one. I wasn't sure who it was, I'll be honest.
Yeah, can we go over that one?
You showed me that one before.
Can we go over that one?
Yeah, let me find it. Yeah, let me find it. Do you know which one it's in?
It's in the 6.
Oh, sequence generator. I see it.
I see it. Design a sequential circuit. Yeah. No, this one. That's not one.
That's not good. Where'd it go? That's not good. Oh, that's better. Oh my god. Oh my god. All right, does this look like the one that you wanted?
No, that one's. I mean, we could do that one.
was the one on page 27 of the slide. It was page 27 of the slide.
Something that might be on the exam is better.
A sequence generator?
Oh, generator.
Sequence generator? This guy. Okay. This guy. You said the other one.
Sequence, oh,
You said the other one.
yeah, because the circuit for that one is like super long.
Oh, this isn't as bad. It gets worse.
Oh, no, not the generator.
It gets worse. Yeah, it gets much worse.
That was not that bad.
Oh, no. It gets much worse. My circuits used to be entire pages long.
No, that's right. If you have one, if you have one, like one group, like one that's odd, it's straight. If you have odd, you have three dots.
Okay, so you wanted this one.
Yeah, yeah. But basically, we were assuming that we have nothing.
Yeah. What type of question do you use? What type of question?
All right. Let's do it. Okay. Okay. Since we kind of already did that, I'm not going to redraw this. I think everybody can figure out how to make that. Right. Okay. So you see how he wrote down these state numbers the same way I did over here? So I put it in the circle, he put it outside. So we're going to label that as what did he label it as? S1. Cool. It makes my life easier. Cool. It makes my life easier. Yeah. So we're going to label S1 and S0. Actually, I'm going to change the way you guys do this. So we're going to set up a truth table. In our truth table, we're going to have our inputs. Our current state, and then this will be all on this side. And then over here, we're going to have our next state, and then we're going to have our outputs. So our flip-flop and our next state are the same thing. Yeah, they're going to be equal to the same thing. Yeah. So I'm going to label so if we look at the question, we have no inputs. So we're just going to ignore that. Our current state is this, and that, right? So we're going to write those down, right? So we have 0, 0, 0, 1, 1, 0, 1, 1. Okay. And since there are, like I said, no inputs, it's impossible to go to anything else. And those are all of our possible values. So then our next state, So if we look at that state diagram, if our current state is 0, 0, what will we go to? Where will our next state be? Correct. It'll be 0, 1. Make sure you pay attention to your arrows. I don't know. I've always done it that way, but you know. Okay, same thing. If we go from 0, 1, what's our next state? All right, and then what next? Yep. Yep. Okay, and then we're gonna follow our whoops. Let me change this. We're gonna drag this down a little bit. Okay, we're going to call this S1 as 0, and then this is going to be D1, D0.
So your next state is the flip-flop.
That's how I write it.
Okay, because in the slide he has the next state. Oh, they're the same thing. Never mind.
Yeah, they're the exact same thing.
Why is it
Yeah.
there? Why is it
Exact
there?
same thing.
Why is it there? Why is it there? Why is it there, bro?
I think it's easier to do it D1 and D0 instead of S star because you're gonna get mixed up. If you don't get mixed up, I'll be surprised. But yeah. Well, like, if we look here, right? Most registers are built out of flip-flops, and the input to a flip-flop is D. So we're technically not doing the wrong thing. I don't know if that made any sense, but So W, X, Y, and Z. We have. So will our outputs be dependent on our current state or our next state?
Wouldn't be on next. It would be on next state. It would be on next. It's next state because it's.
Well, our next state depends on whether we get a clock or not. If we don't have a clock, then our outputs are going to be whatever our current state is. So the answer is current state. It's going to be equal to our current state, whatever the value is. It's going to be equal to our current state. Yes. So this is going to be 0, 0, 0, 1. So this is going to be 0, 0, this is going to be 0, 0, 1, 1. It's going to be 1, 0, 0, 0, 1, 1, 0, 0. All right. Any questions how I got here? Because this is the easy part. Output. All right. So I pulled this straight from right here.
Isn't that given?
Yes, it's given. Yeah. Those are your given values. Yeah. Yeah. Well, it's also right here. So you can transfer that into here. Yes, most likely. Yeah. So since we know that our current state is 0, 0, we copy whatever that output is. And for the next one, 0, 1, we copy those values, and we go on for every single possibility. Okay. And then we'll go ahead and do this. So now we can choose. Do we want to simplify or say screw it and make a giant circuit? Correct. Okay. So what is D1 equal to? How can we simplify? No, you can't simplify it. Look at it. What kind of circuit is that? What is 0, 1, 1, 0? I think someone had it. Huh? XOR. Huh? Yes. XOR. It's yeah. So D1 is equal to an S1 XOR an exclusive OR. Okay. So we're going to do the same thing for D0. So in the big, if you have more inputs, you're going to want to create a truth table. But since these are small enough inputs, you can kind of just eyeball it. Yeah.
So would be, if we had inputs, then we would make, according to current state and.
Yes. So you'd have 2 to the power of all of that. So especially with these, you need to use X's. You need to use you don't care. Use X's. Because at some point you're gonna have 32 bits. And I don't know about you, but I ain't doing all that. Maybe you'll have 64. Maybe you'll have even more. It's gonna get really, really bad. So make sure you use you don't cares, or else you're gonna run out of time on your exam. Did anybody ask any questions? No, we're good. Okay. No. Yeah. So for D0, what do you guys think the most simple value is?
Isn't S naught is just inverted?
S naught?
Or I'm sorry, like D0 is equal to S0 naught.
Yep.
That's what I meant.
I assumed, but
I
you
read the
know.
lower notation as like naught.
Yeah. All right. Then what about W? Similar to what he said?
S1.
Yep. Okay. And what about X? Yep. What is that all? Yeah. So we're going to do S0, S. Yeah. Okay. And then Y?
S1 or S0.
For Y?
No. I'm sorry.
S1 not S.
Yep. Okay, and then finally for Z.
S19.
Yep. Okay.
So what happens if if there's inputs, what changes?
Can you guys chill for a second? I need to hear him.
What happens if there's inputs, what changes?
Guys, what's up?
If there is inputs, what changes?
Okay. So you're asking let's say that there is I don't know, A and B here. Okay. So all that does is, can you get, guys, if you guys are gonna have conversations, just chill out a little. Be quieter, please. So our inputs, let's say, I'm gonna do it separately. So we're gonna have A, B here, S1, S0. So this would require all of them. Require to do 0, 0, 0, 1, 0, 0, 1, 0, and then so on. But let's say, I'm going to change this up and I'll go change it. Let's say for here, instead of no inputs, we have A input and B input. But for this one, we leave it as it is. This one is A, this one is, let's say this one's A not B, and this is B not. Okay. So if we follow this, we know, actually, for future reference, do the current state first and then your inputs whenever you're doing this. What's up? I'm just answering this question. We're just doing what if there's inputs.
Would it not have to be a different question?
Yeah, I'm just going to do this part real quick. Hypothetical. Okay. So we see here that we go from state A to state B no matter what, right? If we look here, there's nothing that's required here other than a clock up. Right. So instead of doing all this, we can erase these here and just put X, X. You see how I got that? You see how? Because there's nothing that requires this input. Yeah. Yes. So we're going to do the same thing for B to C. So our current state is now 0, 1, but the requirement to move on is that A has to be equal to 1. So any questions about that? Or make sense? Okay. So we're going to do A equals 0, B equals 0. Actually, no. Huh? Well, we have to do every single possibility. Yeah. So if we do this, yes, yes. So with this, we know that if A equals 0, we stay where we are. So so with both of those two, that can be turned into an X. Okay. And then for these two, we know that, I'll change this to stay. And then for this one, it'll be equal to move. We'll move to the next state. Do next state. So instead of all that, we can simplify this, right? We can simplify this. What terms are the same for both of them? So for these two, the similar terms is A naught, and then for these two, the similar terms are A. So instead, we could simplify this into, over here, we can go to 0, 1, 0, and X. And then this one, these two will turn into 0, 1, 1, X. And we'll go ahead and do do you want me to keep going? Okay. I'll do it. Oh, do you want me to zoom out? Oh, sorry. He was still taking a picture.
You don't have to do it, just do like circuit for each one of those outputs.
Yeah.
But you don't connect them, like just separate circuits. That's it.
Yeah. I mean, you can connect them. Let's say for one of these, let's say, for example, W and X are the same. Their outputs require the same values. So you can have just one gate. We can have one gate with whatever going into it. This can be equal to W, and this can be equal to X. So in that case, you are technically combining them, but you're saving a gate in doing so.
But we don't have to do that, right?
You should. You want to simplify it. Because he will take off points if you don't.
We're essentially using a register.
Yes.
Wait, so the circuit for that would just be, can you just make the circuit?
Yeah. All right, guys. I'm going to quickly make the circuit because it won't take that long. Huh? So we'll have S1, S0 here. And then our exclusive OR. This is equal to D1. I'm going to keep it as D1 for now, but we'll change it in a second. And then we'll have D0 is equal to an inversion right here. For here. Then we know that W is equal to that. Let's do S1 equal S1 to W. And then X right here is going to be equal to both of them ANDed. And then Y is going to be the AND of at S1 inverted. Okay, so this is how I want you to start it. Do this. Then from here, we're going to change it up a little bit. So we need something to store our value because we need something to store the value of our current state. So to do that, we're going to create a register. So we're going to create a register right here. You can name it whatever you want. So now we're going to copy these. I'll put it right here. Move this down. Move this over here. Okay. So then if we take our S1 and our S0 right here, and we just copy this. So since this one will be our D1 and our D0, instead of just having those go into nowhere, we're now going to put those wires into our register, like so. And then our register will output our S1 and our S0. So now we can't just have those S1 and our S0 just floating out of nowhere. So we need to actually go connect these. So to do that, we're going to do this. We're going to get rid of our S1s, and we're going to wire it up right here. And then I'm going to change the color for the next one. Let's do blue. So we'll go here, and then for this one, we'll go right there. Here. You see how now there's no wire coming out of nowhere? They're all connected together, just like how in this one, or in this one right here, there's nothing. All the circuits are connected together. Yes. If there was an input, let's say we have A right here, that can come out of nowhere, but all the other ones have to stay together. Any questions about that? Because this is probably going to be the last thing we go over.
I think that's the last thing he talked about.
No, there was more, but that was the last thing he like went in depth on. Like he kind of brushed over everything else. But this was like the one he went like.
What else was there?
That was the odd parity checker.
Oh, yeah.
That was easy.
Why would you make that face?
I want to hard.
I don't know what that is. I mean, I can look through it.
I can explain it. It's like when
That's
you
what
have like a string of bits, right? You have a string of bits, and he's like, okay, for an odd parity one, so it's like the moment the first one is shown, first the whole circuit, the output goes odd, right? And then it holds that value until the second one shows up in the bit, and then it goes even again.
Oh, that's not bad.
And then it just keeps going.
And this keeps going even on, and whenever like one shows up.
Okay. So you wanted to do the odd parity one, right? So this one's really easy. So we're going to have our x as our input. We're going to have our x here. So this is going to output. We're going to output even here. We're going to output odd here. That's all it is.
That's it.
Yeah, that's it.
Okay.
Is this be on YouTube?
Yes.
Just the IEEE.
Yes.
Or not this part.
Yep. All right. Just make sure you subscribe to IEEE. Let's get us a play button.
I've already been
No, 100,000. Yes. I think it starts at silver. All right, guys, that's going to be the end of our video here. Thank you, guys.
Thank you so much.